Hello, this is Joshua. I'm going to show you how to sketch non-standard titration curves. I know everyone hates acid-base, but trust me, it's not as hard as you might actually think it is. You can do it. Let's go! Okay, so what do I mean by non-standard titrations? Okay, by that I mean I'll be covering these three in the video today. So this one is going to be a polyprotic acid. So polyprotic acids are any acid that will produce more than one H plus per acid molecule when it ionizes in water. So stuff like H3PO4 is an inorganic polyprotic acid. And then you can have stuff like oxalic acid, which is HOOC and COOH. So that's oxalic acid. That's a weak that's a polyprotic acid as well as it being a weak acid. But anyway, all of these are weak acids, by the way. All polyprotic acids are going to be weak acids simply because the ease of abstracting a H plus from an already negatively charged conjugate base is going to be more difficult. Yeah, so your second dissociation onwards, the Ka is always going to be less than 1. Okay. Now the next one I'll be covering is a titration of a mixture containing two different weak acids. So I can have I could have a mixture of this plus ethanoic acid, or so I could have a mixture of oxalic, or as IUPAC and therefore your A level and IB love to call it, this one is ethane dioic acid, this one would be ethanoic acid. So I can have these two together and then ask you to go and do a titration. We will cover that. And lastly, we will have a titration of an amino acid, and this is for A level only. So IB people, be happy that you don't need to do this. Yeah, across all of these three, the concept is the same concept. Yay! So that means you only need to really learn how to do this once, and then you will be able to do all of these really quickly with enough practice. With an amino acid, there are going to be extra stuff that you need to consider, but it's really not that much. And if you already studied your organic nitrogen compounds topic really well, then you should have no problem with it. I've covered these in separate videos: strong acid and strong base titrations, back titrations, and titrations of weak monoprotic acids against strong bases. And I've also discussed the titration of a weak acid and a weak base in its own video as well. Okay, so this is the allocation of the marks. Okay, normally these sketching of the pH curves carries 3 marks, and it's slightly different from what you would expect out of the normal monoprotic weak acid strong base graph. Okay, so the marks here go to the shape, so you need to have the correct number of equivalence points and buffers regions. Remember that H plus and OH minus react together in a 1-to-1 ratio, right? H plus OH minus becomes H2O. Okay, so this and this react in a 1-to-1 ratio. Okay, and so the important thing to make sure is that, let's say I have so to make sure that every single H plus in the acid molecule is gonna end up being neutralized by OH minus. That means that if I have a titration of H3PO4 for example, then what I'll be doing is I need to make sure that my graph of H3PO4 against NaOH is going to have 3 buffer regions and 3 equivalence points, because I have 3 hydrogens here, as you can see, and that's why I need 3 equivalence points and 3 buffer regions. Yeah. Okay, And so again, as I've shown here, the curve must be flat at buffer regions, like really gently sloping, flat. And then it must be vertical. Must be vertical at the equivalence volumes. Yeah. Then the next thing that you need to do is for your y-axis, okay, y-axis, the pH values at the maximum buffering capacity should be labeled there. Okay, so again, unlike your normal weak monoprotic weak acid against strong base curve, it is not. We do not care about pH at equivalence point. No, we don't care about that in this case, because to calculate the pH values at maximum buffering capacity, you would need you need to construct an ice table, and you probably need to construct that 3 times, and you need to go through the entire process 3 times. That's not gonna they're not gonna ask you to go and repeat the same thing 3 times and waste your time, and it's repetitive, and no. So you only need to label the pH values at MBC, maximum buffering capacity, or half the equivalence volumes. So on your x-axis, it should occur at half the equivalence volume, and the y-axis, that corresponding y-coordinate, should be your pH equals to pKa, right? And that has to do with your Henderson equation, yeah, where pH equals to pKa plus log salt over acid, and at maximum buffering capacity, concentration of salt and concentration of acid are the same, so 1 over 1 is 1, and then log 1 is 0, so pH equals to pKa plus 0 equals to pKa. Right, now equivalence volumes are half equivalence volumes. This is for your x-axis, okay, x-axis, label these correctly. And remember again, because H plus and OH minus react in a 1-to-1 ratio, right, therefore since you're using the same concentration of sodium hydroxide to go and react with this same solution of acid the entire time, concentration is proportional to volume, and therefore all of your volume markings should be evenly spaced at regular intervals. Evenly spaced at regular intervals. Okay? Right. So this is my general problem solving strategy. So I will treat the process as if OH minus will neutralize the acids one at a time. So I don't care where the H pluses came from. Okay, I can assume that the acid with the lowest pKa is gonna have its all of its H pluses dissociated first, and then move on to the acid with the second lowest pKa, and then the third lowest pKa, until everything has been neutralized. Because at the end of the day, everybody's going to get neutralized, so it doesn't matter who goes first, it doesn't matter who goes last, all H pluses are going to be neutralized anyway. And so you can make this assumption to simplify your understanding, right? And the pH graph will prove that accordingly as well. Okay, then after that, the second thing I'll do is I will take care of my x-axis. Okay, so this is my x-axis. I will mark out all the equivalence and half equivalence volumes, and then I will use my pencil to draw dotted vertical lines going up from my x-axis. So like maybe this is my 5 cm mark. I will write that, and then I will straight away draw this dotted line. By the way, yeah, I should probably just put that V over there, yeah, so that I can just draw my dotted line straight up there. Okay, and then after that, the next thing I'll do is I will like sketch my curve. Okay, I'll sketch my curve. Okay, sketch the curve. And then afterwards, I will mark out the pH at the MBC on the y-axis. So let's say I just make up a y-axis here. Oops, I cut through my text. Silly of me. This is my maximum buffering capacity, perhaps. Then I would just put a 2.3 over there. Yeah. Then that is my last thing. So, and make sure again the shape of your graph should be flat at the buffering region and vertical, flat at the buffering region, vertical at the equivalence volume. Okay, and then this is a graphical representation of that, where I have shown you how. So basically, I assumed that I was titrating a tribasic weak acid, H3A. Please do not assume that this is a real acid because I just made up these pKa values for your convenience, and you can see it's also not ready to scale lah. So I didn't start off at like anything below 1 because it's a weak acid, okay? And then I assumed that each H would be come off stepwise. So at this point, H3A is being neutralized. Looks like I can't change the color on this thing. And then at this point, H2A minus is being neutralized. And then at this point, HA2 minus is being neutralized. And at this point, this is A3 minus. So they neutralize one at a time. That's number one done already. Okay. It's number one done already. Then after that, what I do is I mark out the equivalence volumes, and to help me out, I just label them as equivalence volume or half equivalence volume, right? I just mark them out, and then I use the pencil to draw dotted lines going up. And then after that, the third thing, I've done the second thing, yay, okay. Then the third thing I do is I sketch out the curve first, and then from the curve, right, I identify my maximum buffering capacity points, there, and there, and I jot my horizontal lines cutting the y-axis over here, and then writing down pH equals to pKa at these particular values. So that's it. And in total, once you practice, this thing won't even take like more than 2.5 minutes. For the titration curve of a polyprotic acid, we are going to use the example of a 0.1 mole per dm cube solution of phosphoric acid titrated against sodium hydroxide solution of similar concentration. Okay, so these are the successive pKa's of phosphoric acid given here. Okay, and how we work about it is we don't even need to decide who has the lowest pKa. I mean, it's obvious that 2.1 is the lowest number of the pKa, but we don't need to decide who gets neutralized first, because at the beginning there is only one acid, H3PO4, and this acid has a pKa of 2.1, so obviously that will get neutralized first. So all of the OH minus will neutralize all the H3PO4 to H2PO4 minus in this step over here, right? And then after all of this H3PO4, all of it is gone, then it will start to neutralize this group with a pKa of 7.2. Ayo, 7.2. And then after all of him is gone, then we will start to neutralize this guy with a pKa of 12.3. And let's go to sketching the graph. Let's go over now. Let's begin sketching the graph. So over here I have already put out the standard pH and NaO against the amount of alkali added. Now I'll just label the volumes: 5, 10, 15, 20, 25, and 30. Since there are 3 equivalence points, I will have the correct number of equivalence points. So my equivalence points there, no, that's not equivalence point, equivalence point, equivalence point. Then after this is my half equivalence points for the corresponding ones. Yeah, so we need the correct number of equivalence points and half equivalence points. Take note, that's the first thing. Let's delete all those. Let's go. And then the next thing I'll do actually, right, is already since I've just labeled this on the x-axis, I will proceed to start to shoot my vertical lines up, because that's just how life works. Yes sir, that's how life works. How did this thing... Meanwhile, I don't know how this ruler works. Sometimes it's big, sometimes it's small. Okay. Then you'll go on to make this one. So I'm shooting my vertical lines up. That's my second step, labeling the x-axis correctly. Oh, by the way, you might want to make these last ones super high, or like as you go towards the right, your dotted lines get progressively higher, obviously because your pH will increase as you add more base. Yeah, and then now that we have that, I'll just leave the ruler aside. This is a strong, this is a weak acid, phosphoric acid, so I'm not gonna, add in, I'm not gonna start too low. I will, oops, start here, shoot up, oops, yeah, okay, I will start slightly high, shoot up, okay, then I'll repeat the process for that, shoot up, okay, and then repeat the process for that, gently sloping, shoot up, and then flatten out, because as you add more sodium hydroxide at this point, as you add any more sodium hydroxide, while you are adding more moles of sodium hydroxide, you're adding more DMQ of water as well, so the concentration overall remains constant. Yeah, okay, then the last thing we've got to do is just to label in the pKa values, which I put in on the page before this. So let's just go flip this back off. Okay, oh, this was 2.1. Yeah, so it's 2.1. Then let's check this one out. This one was 7.2, and this one was 12.3. And actually that's it. That's all there is to sketching the polybasic titration graph. Let's go to a titration curve of a mixture of acids, and I'm going to titrate a mixture of 0.1 mole per dm cube malonic acid and 0.1 mole per dm cube of 3-hydroxypropanoic acid, using equal concentration of NaOH. Again, I've just kept concentrations constant so that I can use the terms amount and concentration interchangeably. Okay, but if life decides to screw you over, and the teachers, the setters, especially for Singapore A levels, decide to cook something up, you need to be careful, yeah, to make sure that you calculate the volume required by first using the moles. Okay, anyway, you don't need to care about this. This is such a complicated thing, yeah, but I've given you the structure over here, right, of the various acids. Okay, and I've also identified the pKa's. Okay, and so remember what I said about in increasing order of their pKa. So that means that this group with the lowest pKa will be neutralized first, then this group, then this group. So what does this example prove? Actually, right, it is not the sense that this group, malonic acid, just because it has a stronger pKa1, will be neutralized first, this, the order of this one, then this one, then this one. No. So the first neutralization of malonic acid will occur, then the neutralization of 3-hydroxypropanoic acid, and then this neutralization, because it occurs in order of increasing pKa. So there we have it. And note again that the pH at the respective maximum buffering capacities equals to our respective pKa's. Okay, so now let's get to the graph sketching of the mixture of the malonic and 3-hydroxypropanoic acid, the long name acid. Okay, anyway, so I'll just write down the pKa's. So for malonic, I'm just gonna call them M and 3H lah, huh? Okay, just gonna call them M and 3H. So this one has 2.83, the next one is 4.51, and the last one is 5.69. Those are the pKa's of the, yeah. Okay, so now with that in mind, we can go ahead and sketch our pH curve. Now make sure that you do this in very light and dotted pencil, because if the IB or A level markers end up seeing this sort of really dark colored lines, or if they are like not dotted, they will start to deduct marks for your presentation, because that's like, you can't make other markings. It's kind of like your maths. Yeah. So let's, oh, my ruler's not doing well today. Okay, then the last one, just shoot up really high, and then the last one, you would, doesn't need to be exact, but just try and make sure you create a nice straight line, and please use a ruler for this in real life as well. Then the next thing I would do straight away is start to carve out my graph. Straight away, a rather flat region that only shoots up at the neutralization point. Again, another one, a really nicely gently sloping one that shoots up. I don't know why. Okay, you need to connect these nicely when you draw these in the exams. I'm drawing with a finger on my iPad, so once I get an Apple Pencil, hopefully things change. And then this last one shoots up and then tapers off. And again, because you're adding the same amount of sodium hydroxide, but the volume is also increasing, the concentration after this, and hence the pH remains constant. Oh, I meant to use this. Oops. Okay. And then the last thing we will do again is just plonk our pKa values at the maximum buffering capacity. So 2.83. Threes are the most challenging number to write on an iPad, by the way, with your finger. It's a difficult hand motion. This one will be 4.51. Okay, and this last one is going to be 5.69. What ugly numbers I am writing. 5 point, aiyo, 5.69. And there we have it. There is the graph of your mixture of different weak acids. There's your mixture of different weak acids. So for the titration curve of an amino acid, it's pretty much the same as the previous two cases, except that we're gonna have to consider two more extra things. Okay, so what form of the amino acid is present? Okay, that depends on your initial pH, because each group, each amine or each carboxylic acid group of the amino acid is gonna have its own special pKa, and so you will need to determine if that group will exist in protonated form or not, because that will influence the number of neutralizations and equivalence points that you have on your graph. Okay, so if the pH is below the pKa of that specific group, then the group exists with the proton H plus attached to it, COOH or NH3 plus. Okay, so COOH or NH3 plus, sorry, NH3 plus. Okay, then this one, if the pH exceeds the pKa of that specific group, then it's deprotonated. So that means it's COO minus or NH2. Okay. And I cannot erase it here. Okay, just by NH2. So then the second thing is what we need to deal with. Okay, this is the first thing. The second thing we need to go and determine is what is the structure of the Sviter ion. Okay, so the Sviter ion of a amino acid is when the overall charge is 0, but there are no overall the charge is 0, but there are localized charge centers at like the NH3 plus and the COO, but the net sum of all those charges is 0 at each group. So you need to go and figure out how many protons you need to remove in order to obtain the Sphighter ion, and if basically that corresponds, the n deprotonations required corresponds to the nth equivalence volume, the pH at the nth equivalence volume being the isoelectronic point. Okay, and so the important values, obviously this is the one that you need for every single pH graph, even the monoprotic weak acids, like everything, all weak acids, you need this, and this one is for amino acids only. Okay, yeah, and then let's move over here to this example. Okay, let's move. So I'm titrating this 0.1 mole per dm cube. Take note of the fully protonated form of aspartic acid using equal concentration of sodium hydroxide. So I've given you here the structure of aspartic acid in its fully protonated form and some helpful info. So these are the pKa's of the respective groups. Okay, 1.8, 3.65, 9.6, and I've also circled them out here. So obviously by going from our very important golden principle here, right, you will neutralize the acids in increasing order of their pKa. This is the one concept that will hold true throughout your entire, all of the graphs. So there we have it. This will come off first, followed by this, followed by this. Okay, as I've written here. And remember once again that the pH at the respective maximum buffer capacities equals to pKa, and the pH equals to the pi at the Sphighter ion at the volume where you have created the Sphighter ion. And for this one, if this is already a +1 in its fully protonated form, then let's see, one of these guys has to come off, so you could create a COO minus with a -1 charge. So this guy is going to come off first, this H plus is going to come off first, okay, and therefore you will create a minus charge on this one, right, and you will create -1, and overall this will create 0. So the Sphighter ion is going to look like this. Yeah, and let's go on to sketch the graph. Okay, so over here I have already just put down that same pH graph against volume of sodium hydroxide added, and then I've also included here a diagram of the amino acid along with the pKa's of the various groups. Okay, so now that means we can save time and directly get started with drawing our vertical dotted lines. Okay, 5, 10, 15, 20, and 25 and 30. Okay, let's leave the ruler to the side first. Okay, I'll zoom in and then we can begin. I'll zoom in real big. Okay, and then because the pKa of that group was actually 1.88, right, I will just start quite low, just because in order to even reach that point you need to be at 1.8, which is already quite low, and then I'll shoot up. Okay, that wasn't exactly there, but be careful during your exams. Okay, then over here I'll do the same thing, a gently increasing slope followed by a sharp increase. Okay, oops, and then this one you should have this. Oops, I use a thicker line so you can distinguish my graph from, yeah, and then after that, that should taper off to be a horizontal line. You see? Yep. And so now the last thing that we need to do is just to label the important pKa values, really. Oh, my ruler is gone. To get a new ruler. How unfortunate. Whatever, I don't care. Okay, so that is my first pKa value. That is, oh, I have this very large size. I don't want that. And then lastly, I have this one. Okay. And then don't forget that okay, first let's label this. Okay, so obviously that's gonna be 9.60. That's gonna be 3.65. That's gonna be 1.88. But don't forget, this is an amino acid. Okay, this is an amino acid. Okay, and so there will be an isoelectronic point. And what do we call the isoelectronic point? That's the point where the pH where the amino acid exists as a Sphyter ion, and the Sphyter ion will carry overall no negative or positive charge overall, even though there can be localized centers of charge. So that will be where if you have this plus over here, okay, if you have this plus over here, then this one of these needs to be a minus, and it's going to be this one that becomes a minus since this one comes off first because it's a lower pKa. So the Sphyter ion will be NH3 plus COO minus, and this one is doesn't change. So this is the Sphyter ion. Okay, and so therefore the Pi equals to pH equals to 2.80, if I'm not wrong. Was it 2.80? Hope so. Yes, it was 2.80. So therefore I can just grab my ruler now, and I can just find the middle of the equivalence point, right? What you want to do is find the middle of the equivalence point and just draw a little line over there. 2.80 Pi equals to 2.80, and that's it for the titration of a amino acid. So yeah, that's pretty much it, the basic idea for sketching non-conventional, non-standard pH curves. It's really not that difficult. It's just a mechanical process that really, in my opinion, is actually easier than sketching the standard pH curves. Yeah, because you don't need to use ice tables to calculate pH of the initial pH of the acid or the pH of the salt. Yeah. Anyway, these are some of my last tips for sketching non-standard titration curves, right? My tips: drill practice is essential. Really, drill. I know some people, some teachers might be like saying that it's not good to mindlessly practice, or it's not good to drill and then just do it for the sake of doing it, but I disagree. What I'd say is that at the beginning you are mindfully practicing because you have to be conscious to make sure, oh, am I doing this correctly? Am I applying the steps that I've just told you about correctly, right? And you do it enough such that it just comes naturally to you because you've just done it enough. The closest analogy I would have is playing the piano, right? Because at the beginning your fingers don't know what they're doing. It's just like your mind doesn't know what to do, right? So your fingers don't know what to do either, and you practice, you get used to it, you get the grasp of it. The process comes naturally to you. It comes smoother, it comes quicker, you don't make so many mistakes. And so one day you can just like how if you've been practicing something, a piece, for months, weeks, or like years, you can just sit down at a piano. If you've been consistently practicing the entire time, you can just sit down at any piano and just play that thing out loud without having to really think about it, because it's kind of like locked in your long-term memory and muscle memory. And you can do the same thing for acid-base curves because it's the same process as I've demonstrated throughout this video. So until you can do this naturally and confidently, yeah, and that's why I suggest what I use at the bottom. So practice sketching 2 curves a day. I don't even care what it is, right? I will just practice sketching 2 curves, and I'll just use various weak acids. I'll mix and match, you know, maybe choose mixtures of one weak acid, and the next day pick another 2 weak acids. So practice using a mixture of 2 weak acids, and then maybe the next day I do a mono-basic weak acid with a monoprotic weak acid with a tri-basic weak acid like phosphoric acid and ethanoic acid. Yeah, then that would be a good one to practice. And in this useful website I have had, this is where you can go and grab all their pKa and their pi values for amino acids and a couple of other weak acids. Yeah, so go to this website. I'll put the link in the description below. Okay, and if your school, especially for like the Singapore A levels, especially if you want to practice for the school coming out to trap you and trip you over, what you can do is you can make it as complicated as possible. So sketch them for mixtures of amino acids or mixtures of multiple polyprotic acids. Although it's not really likely to come out, the most you get is a mixture of dibasic and a monobasic weak acid each. More likely that you should practice is this one, where you vary the concentration of NaOH to be different from the concentration of the acid. This is where they love to screw students over, because in this case volume is not there's not interchangeable with concentration. Okay, volume is not interchangeable with concentration when your concentration of NaOH does not equal to your concentration of acid. So this is something which I would encourage you to do more. And this one, if you're just either feeling insane, feeling bored, or you know, just want to make sure that like you get the correct number of curves and stuff, but really it's the same process. So you want to challenge your stoichiometry for this one, and challenge the real part where you got to be really careful is this one. Yeah, okay, that's it for this video. If you have any questions, don't hesitate to write them down in the comments section below. Comments, suggestions for improvement. I'm receptive to all feedback. Don't worry, just write it there. I won't bite, it's okay. If you want to contact me, you can also write to my email at the address I've listed here, and you can also follow me on Instagram here at JoshuaY2003. Yeah, and whichever platform you write to me on, it's fine. I'll respond quickly, generally within 1 or 2 days if I'm free or if I'm not studying for some exam. And I won't bite. I like helping people. So yeah, do give this channel a like, do give this video a like, do subscribe to the channel, share it with your friends, and do let me know what you'd like to see next, because I just picked this topic because everyone was complaining about it to me recently. So I will create videos in the order of to suit people's needs. Yeah, so thanks for watching this video, and I hope that you stay to watch the next one when it comes out. Bye!